Hey everybody, it's me, BiBenBap. So, hope you guys are enjoying your day today, unlike myself, since the weather's kind of pretty depressing over here, and it might do the same thing for tomorrow as well, so the weekend's nice. So, before today's video starts, I actually just want to make a little bit of an announcement. I created a TikTok account, so you can follow me at my handle, bi.ben.bap, and you can actually find it in one of the cards attached in this today's video. You can find it in the link in the description below. It's under my channel banner too. That hyperlink is attached there if you want to navigate through there, or even in my community post that I made that announcement yesterday as well. However you want to navigate, it's up to you. So it's basically just me just trying to branch off into other platforms, well, mainly TikTok being the big one, so that I can actually solve shorter math problems for fun, typically the easier ones that I personally feel that it wouldn't make it as a standalone YouTube video on its own. But I also try to add a little bit of humor to the mix, be a little funny for the memes, because it's TikTok, why not? So give it a follow if you haven't. Expect some I have a couple problems in mind that I actually want to post on TikTok, the shorter ones obviously, and a little bit of the funny ones too. So give it a follow, and then once that notification pops up, then great. But then I just want to say thank you guys for your support. I made the announcement I reached 1,111 subscribers. That's quite a unique milestone to make that announcement. So let's see if I can do the same thing again if I reach 11,111 subscribers. So, if that happens, we'll see what happens. But yeah, so thank you guys for your support. If you haven't subscribed to this channel, go ahead and subscribe. Leave a like, comment, follow my TikTok for, unique content. And without further ado, let's actually just jump in today's video. Okay, so welcome back to another video. So here today we have this pretty long limit. The limit as n approaches infinity of the nth root of these two following products of the partial sum. So the first piece we have is a partial sum of k squared divided by 2k squared minus 2nk plus n squared. And then we have a second one, the same partial sum, except we have k cubed divided by 3k squared subtract 3nk plus n squared. So we could be here all day and actually just expand this entire sum and see what kind of pattern we can figure out in order to get the the true value we want. But let's not actually do that. Otherwise, this video might probably take I don't know, probably a day in length. But it's actually a simple limit than you think it is. And if you pay attention closely, for example, if we're looking at a specific sum, we don't actually have to look at one sum and evaluate that, sum we're looking at exactly. Instead, we can actually rewrite this a little bit simply. Same thing, we're going to do the same method over here, because if we take those functions, or rather those partial sums, and make it a little bit easier to understand, then simply at the end, once we find what each of those values of those sums are, we can actually write it in a form of another product in terms of simplification that'll still be the same as what we were given before. So to take away that gist, we're actually going to take a look at these two, sums here, not evaluate them exactly the way it was given, but in another form where it's a little bit easier. Then after achieving both those values, multiply it with another, variable that's actually close to that, with the products together, it'll still give out exactly what we want. So let's actually just jump right in. So suppose if we call this entire limit capital L. So let's first look at this following, the sequence of this partial sum over here. So I'm just going to call this capital I sub n, and we'll say that the sum we're going to look at specifically is supposed to be 1 divided by n squared, and then multiplied by the partial product. And this is supposed to be n over here, since this is supposed to be with sequences. Eventually later we're going to take this limit and then we get an infinite sum. So that's a basic takeaway. The same method from over there as well. Our first index k is equal to 1. Then we have k cubed divided by 3k squared, subtract 3nk, and then add this with n squared. What we can do is we can actually divide an n squared to both the numerator and denominator, but to make things a little bit easier after that, I'm actually going to distribute a 1 over n into the numerator. And so performing all this simplification, we'll have new following. So we'll have 1 over n, then multiply by the partial product again, k is equal to 0, or k is equal to 1, and then all the way up to n. And so let me write down this denominator first before we continue forward. So after performing all this, I'll group this after dividing n squared to both sides, and and then that 1 over n will be moved to over here. So we're really looking at the denominator first. So 1 divided by n squared to both sides. I'll group this as, because k squared and n squared are both, share the same, exponent, the 2. So we'll write it as k divided by n, then quantity square. Then on the bottom, then one of the n's will cancel. Then we still have 1 over n on the bottom, so this will be 3 times k divided by n. And then next we have just plus 1. And then on the bottom, we do the same thing, divided by n squared, but I said I was going to move the 1 over n to this side. And so now we have the following. We'll have just k divided by n, and then the exponent 3. So where is this coming from? Interestingly, if we use the definition of the definite integral, if we take this limit of the partial sums of each of those terms with a multiply with the length of each of the subintervals, if you make this observation correctly, we can actually write this as the following. So that would actually mean that I will afterwards taking the limit of both sides. So now the limit as n approaches infinity of capital I sub n, we would now have this new definite integral of, well, not this new, but we will have a definite integral of from our bounds from 0 to 1, and then we have our function, our integrand x cubed divided by 3x squared, subtract 3x, and then add this with 1 dx. And you can see that for yourself that if you, again, using that definite integral definition, you'll see that these two are equivalent to each other if you put in the right pieces. How do we evaluate this integral? Well, you'll notice that we have an x cubed on the numerator and an x squared on the denominator. That means we have a higher order or the degree. So in order to fix this a little better, we're actually going to perform a little bit of some long division. So polynomial long division. So we have a divisor of, the denominator and the dividend, which is the numerator over here. So we write this as 3x squared minus 3x, and then add this with 1, and then this is being divided by, or that's the divisor for the dividend x cubed. And to put things a little simple, I'll put this as plus 0x squared plus 0x and then plus 0, just so we're dealing with these terms, nice, easy. So first, you'll notice that I can actually multiply a 1 over 3x into our divisor. So I'll put a 1 over 3x. If I just perform the multiplication distribute over here, so we have a x cubed, then this will be minus x squared, and then add this with 1 over 3x. And if I just subtract all this quantity down over here, then the x cubes will cancel each other out, and then we'll just switch the signs for the rest. So over here, this will become a positive x squared, and then next we have a minus 1 over 3x. Now what I can do is, now we can continue forward, so we can actually add a 1 over 3 to the over here, so multiply that. So then this would complete that this is just x squared, and then on the bottom this will be minus x, and then now we have add this with 1 over 3. Then if I just subtract the terms, so the x squares will cancel, then we add the x to here, so this will be 2 over 3x, and then minus 1 over 3. But that's all we can continue from here, because obviously we have a 0x and then x squared over here, so we cannot continue forward from what we have in this so far. So this would mean that this is actually considered our remainder. And so when it comes to long division of polynomials, so this is what we can divide into, but then our remainder is supposed to be divided by our divisor over here, implying that now we have our new integral. So that means our new integral, so from 0 to 1, I'll just rewrite the same thing again. So x cubed divided by 3x squared, add this, or rather subtract 3x and then add 1 and dx. So now we have our new integral, and because of this is actually with a sum of these, it's polynomial again, and it's by continuity and using linearity, I can split this up into 3 different integrals, the sum of 3 integrals. So we have one for 0 to 1 of, first we have, I'll write this as x divided by 3 dx, and add this with our second integral. So this will be 1 over 3, then dx, and then the last one we have is our remainder, so this is plus the integral from 0 to 1 of, now I can actually, there's a 1 over 3 on both the, that can be factored out over here, so I can just write this as 2x, subtract 1, and then divided by 3, multiplied by our divisor, the 3x squared minus 3x plus 1, and then dx. Now we just have to calculate these three different integrals, and obviously we know that this is very simple to see that the first two integrals can be easily calculated. I'm not just going to write this out separately without having to put out the calculations. So 0, 1 of x divided by 3 dx. Obviously you can see that by just calculating that, we're going to get a 1 over 6. And a second one, what is it? The integral from 0 to 1 of 1 over 3 dx. This is going to just equal obviously 1 over 3. And so the last part we have to calculate is this thing over here. So this is very easy to see that you just perform a u sub. U equals 2x minus, or excuse me, that's supposed to be the wrong substitution. We let u equals 3x squared minus 3x plus 1. du is indeed just equal to, what is it, 6x minus 3 dx. And if you factor this out properly, you can actually factor out a 3 to both sides and then divide the 3. So now we'll have 1 over 3 du is just equal to 2x minus 1 and then times dx. Okay, and then from here, you can just see that now we have, put the 1 over 3 outside and factor that 1 over 3, so we have a 1 over 9. I'm gonna move over here. So 1 over 9, then our, now I'm not gonna compute the new bounds, I'm just gonna skip that step and we'll put back the substitution for u later. So we see that we have, let's see, the dx will cancel, so that's a du on the top and then the u on the bottom. So du divided by u, and then this is just equal to 1 divided by 9 ln. I'll stick to the absolute value in this situation. So this will be 3x squared minus 3x, and then add this with 1. Then we evaluate our bounds from 0 to 1. Obviously, you see you plug 1, so 3 minus 3 is 0. Add 1, ln of 1, that term will just completely vanish. Then we have 0, 0, 0, then plus 1. So, you know, ln of 1, so this is just going to equal 0. And so therefore, and I'll write this, just the limit as n approaches infinity of I sub n, we just add the terms together. So 1 over 6, add this with 1 over 3, plus 0, this is just going to equal 1/2. And so we have just figured out our first, sequence of our sums. So I sub n is equal to the limit as n approaches infinity of I sub n is just going to equal 1/2. So far so good that we have computed one of the following. So we just have one more to solve, and that is to do the second one. So next, we're gonna jump into j sub n, and so I'll let j sub n, we'll let this equal to the following, we'll call this 1 over n, and then multiply by our partial sum, so n, and then k is equal 1 of, now this will be k squared divided by 2k squared minus 2nk, and then add this with n square. Then we see that we're basically just applying the same thing that we just did before, this exact same method. So now I can actually, except we're just skipping one step, and we're not doing that one step where we have to just move that one n into the numerator, because we don't really need to do it in this situation. So if I fix this up, then we would just divide the n squared to both the numerator and denominator and group it just the same way like over here. And you can probably see where I'm going with this in the next step, but I'll explain it again one more time for where we're going. K is equal to 1 and then n, so let me write the denominator. So we have 2, then k divided by n squared, minus 2, then k divided by n, and then subtract 1. Let me actually just, how about I just move this to the next line instead, since it's taking up a lot of space. And so now we see that here, it's just doing the same thing before. If we actually just apply, yeah, that's fine actually. Actually, after just noticing the same observation, just like what we did before, we can actually just apply the definite integral after taking the limit of both sides. So I'm going to write this as the definite integral 0, 1. And so we see this is just x squared divided by 2x squared minus 2x plus 1 dx. And let me make a little justification to say here that as we take the limit as n approaches infinity over here. So now you'll see that with our definite integral that's equal j sub n, the limit as n approaches infinity of j sub n. So again, we have a x squared over x squared, same degree. We can still perform the long division. So that's what we're gonna do. So next we have 2x squared, that's our divisor. We subtract 2x and add this with 1. This is being divided by x squared. Let me add this with 0x and then plus 0. Then we just apply the same thing. Let me just add a 1. Let me multiply a 1/2 on the top. And then over here, we're going to get that this is just x squared, then minus x, and then add this with 1/2. We subtract everything together. This cancels. Then that'll be an x. And then right here, this will be minus 1/2. And after that, we can't go any further from here. So this actually means that this is actually going to be our remainder. And so with this new integral, then that means we have, so I'll write the same thing again, x squared and 2x squared minus 2x plus 1 dx. Then if we just do the same thing, again, it's a sum. So we can actually just apply linearity and write this as a sum of two integrals. So we have the first integral from 0 to 1 of 1/2 dx. And add this with another integral, 0, 1. This will be x minus 1/2, and then we just divide this by our divisor, 2x squared minus 2x plus 1, and then dx. So obviously we can see the first term over here, the first integral, that's easy to calculate. So we put this as, so 0, 1, 1/2 dx. That's obviously going to just equal 1/2. Then next over here, we have to apply the u substitution over here. So we'll let u equals 2x squared minus 2x plus 1. du is going to equal 4x, subtract 2 dx, and then factor this 4 from both sides. So we have, and then divide the 4 to both sides. So we have 1/4 du is just equal to x, and then subtract 1/2 dx. Perfectly, we can actually just make that substitution. And so I'm just gonna do the substitution. I'm not gonna compute any new bounds. So this will again still be a du divided by u, and again divided by 1/4. So over here now we have a 1/4, then multiplied by ln using absolute values in this situation, 2x squared minus 2x, and then add this with 1. Evaluate this from 0 to 1. Obviously, you see you plug 1, so 0, 0 plus 1, ln of 1, 0, plug 0, 0, 0, 1, ln of 1, 0. So that means this is just going to equal 0. And so therefore, we say that the limit as n approaches infinity of j sub n, which is this integral over here, then was just going to equal, that's supposed to be a 1/2 over here. So 1/2, and it's actually just going to equal just 1/2, just like that. And so we actually just found our both I sub n and j sub n, and now from here we can actually make the substitution we want to. So now the final step is actually simple. So now actually we just gotta take this limit of our capital L. So we call this capital L actually. So L is going to equal the limit as n approaches infinity of the nth root. So that would mean it's our I sub n. Then we have a 1/n squared. So basically I'll just multiply the n squared. So this will be n squared multiplied by I sub n. And then multiply, so our j sub n, we started with 1/n. So I'll just multiply n to that. So n and then j sub n over here. Okay. And then we actually found our sums, and it's also using the continuity of square roots. Well, of course, they have positive for 1, because you can't have a negative square root in this situation. Then I can just combine the n squared and n2 together, and then the I sub n and j sub n, separate those n roots out. So in other words, we will have the limit n approaches infinity. So we have first the nth root of n to the power cube, and then we multiply by the nth root of I sub n, j sub n. In this situation, if we plug that this is just 1/2 times 1/2, that's 1/4. But it's just 1/4 raised to the power 1/n, which if you take that infinity, then it's going to approach 0. And so therefore, this is actually just going to equal 1. So now the last thing we have to do is just calculate this limit over here. But easily said than done. We can actually, using by continuity, we can actually just take the natural log of both sides. So I'll say the ln of L is basically just equal to, so let's see, this is 1/n, ln of n cubed, which in other words, just multiply the 3. So this is just the same thing as 3 divided by n to the power, well, I also need to take the limit too. So actually, let me go back and fix that up. Now it's just, okay, so we said 3. So that means I'll put this as 3n and then ln of n. Then I just take the e base to both sides. So now over here we have capital L is just equal to, and then continuing on with that continuity of e, it's continuous everywhere from the reals. So it's just e, and then we just take the limit as n approaches infinity of 3, and I'll write this ln of 3 times ln of n and n divided by n. Obviously, you'll see that we have a, you plug infinity for both the numerator and denominator. We have an indeterminate form of infinity over infinity. Of course, we can actually use L'Hopital's rule. Take that derivative, so the derivative at the bottom is just going to be 1, and on the top it's just 3 divided by n. You take that limit again, then you're going to get that this is just going to approach 0. So this is just e to the 0, and so therefore L indeed is just equal to just 1. And just like that, we have finally computed our long limit. I know I said that was actually not that difficult, which it's not, but it actually took a little longer because I just want to make the justification steps for everybody to, understand. And really, I guess I should have left that exercise of these, integrals to the definite integral calculations for yourself, but I think that would have left a lot of unanswered questions for, I guess, most viewers. You would have never thought that long division, I guess, was the way to go. So a good thing I did this, so I hope that clears up any sort of confusion. So, yep, that's pretty cool if you ask me.